Okay, so we're the K in the rate law. K is the rate constant. This is number 19. Remember I told you on the previous notes. So we need to clarify a few things because you're going to see these in multiple choice questions. And I don't want you to get it wrong. Things that affect the rate constant are everything that speeds up a reaction, like in How to Get a Date for the Dance, that you've watched multiple times, except for concentration, because concentration is already in the rate law, so that part does not take effect. But temperature, particle size, or surface area, whichever way you want to think of that one, and catalyst, they all factor into the K. So I'm still trying to figure out in your problem set why one of them included the catalyst in the rate law. I'm still trying to figure out why they would do that, because typically catalysts are not supposed to be in the rate law. They only affect the rate constant, okay? So don't confuse that with equilibrium K, the larger K, the uppercase K, that's only affected by temperature. And you will see these in multiple choice questions. I didn't want you to get them wrong. Okay? So keep that in mind there. Any questions? Okay, moving on. Review question. Good times for you. Just kind of like in your problem set. You're given the data here. You're given the mechanism. Which step is the rate determining? And please explain. Okay, so let's see here. We're looking here, what experiments can we use for ozone? You can use what? 1 and 3 works, definitely. And yes, you could have also used 2 and 4. You could have done either, because the other reactant is not changing in either of those cases. But you'll see it comes out to being the same thing if you did it either way, because we're doubling from 1 to 3, and also you see the rate is also doubling. So if we have the concentration of ozone is 2N and the rate is 2, then N has to be first order. Okay? I'm not writing out all of the division and all that stuff, but that's basically the gist of what you're going to come out to getting. And then over here, same thing would have happened though if you did this one. That doubles. 2x goes to 4x, it doubles as well. So it would have ended up being first order. For NO, what are we going to do there? Yes, we can do 1 or 2. Or you could have done 3 or 4, because this one doesn't change there. So once again, you see that you're going to get 2m equals 2. So m is also going to be first order. So if we actually write out the rate then, the rate law, it's going to be K, ozone, and then nitrogen monoxide. Okay? Okay, so which one's going to be the rate determining step or the slow step? You're looking here at your possible reactants. The only one that has those two together is going to be the first one. So this one would be your slow step or your rate determining step. Okay? Based off of the rate law that you got from the experiments, the data. It's all data driven. Any questions? Yes, Michael?
Why is the slow step?
Because we're comparing it with the rate law. The rate law, we figured out both of the reactants are first order based off of the data. So they are both first order. You look at the possible steps here. Which one has both of them there just one time, basically? And the only one that has both of them there one time is step 1. So that's got to be the rate determining step or the slow step. Okay?
So there was a coefficient in front of like
Well, you're not going to have a coefficient in any of the mechanisms really like that,
Okay.
except for maybe the first step, because it's going to have all the intermediates and things distributed throughout. So you wouldn't see that very often. Okay, it really is that easy. You take the rate law, look for the reactants over here. Okay, there isn't any equilibrium here either, so you're really not looking for a substitution one either. Okay. Now for the differential graphs, and there's lots of graphs that you're going to be seeing. So you need to really be paying attention to what is on the y-axis and what is on the x-axis. You see right here, this is rate versus concentration, okay? And this is the differential ones where we said that 0th order is going to be the no change, right? So that's why it's just a straight line across. The first order is going to be what? Anybody remember?
Same change.
Same change. Good. And so it should be the same change. It should be very proportional, nice straight line slope. And then second order is anyone? Square of the change. Good. Square of the change. Okay. So you're going to see graphs though today where we're going to be concentration versus time. You're going to see natural log of concentration versus time. You got to be very careful in watching the way the axes are labeled. This is talking about differential rate laws. The next set of graphs you're going to see are all in the integrated rate law graph category. And obviously you would assume that in your test and on the AP exam you're going to see lots of graphs in when referring to kinetics. Okay? So be very analytical about looking at the graphs. And you see, yes, square of the change here, just to note, obviously is more exponential curvature going on there. Okay? All right, you don't need to rewrite this down. This was in the last notes, but just to give you big heads up again, rate versus concentration was basically differential. Integrated, now we're looking at concentrations versus time. Concentrations versus time. So it's a totally set of new formulas and different idea of looking at the data. Okay, so you don't need to rewrite that down. However, what you do need to know, information about the relationship of concentration versus time. That's one of your questions. Okay? So you do need to know that. How can we compare which order of the reactant using the integrated rate law? We can look at the graph that gives us the straight line. Now that doesn't mean anything right now, but it will later on, because you're going to be looking at the different orders. 0 order, first order, and second order put different things on the y-axis. And when we look at their comparison with time, one of the 3 graphs will come out to be a straight line. Whichever one does come out to be a straight line, that's going to be the order of that particular reaction. So, one of them's natural log of the concentration versus time. That's first order. Second order is the inverse of the concentration versus time. And 0 order is just the concentration versus time. So we'll be graphing them in our calculator to make it easier. And when we do that, we'll be able to tell which one comes out with a straight line will be the order of the reaction for the rate law. Okay? All righty. Okay, first order rate law. Okay, the integrated rate law formula is right here, but you'll also see it written like this. It's actually on the formula sheet like this. And this is supposed to have a T next to it, by the way. So you'll see it on the formula sheet like that. In Kinetics, they do give you a few of the equations on here. They give you the first order integrated rate law, they give you the second order integrated rate law, and they give you the first order's half-life equation. That's pretty much all they give you here for the kinetics little section on the sheet. Okay. Now, obviously, this one over here, just have a little t there. Concentration of A at the time. K is the rate constant. T is the actual time. And then the concentration of O there, that's always when it has a little O next to it. That's the initial concentration. Okay? As you can see here, it kind of looks like another equation. I don't know if you can pick out those variables and see them. I know naturally, right? However, the natural log of the concentration at T is supposed to kind of look like the Y of the mx plus b, here. And then K is the slope, M, T representing the x variable, and then B over here, the y-intercept. Very similar. And you'll be looking kind of, like I said, for straight lines and stuff here, looking at those kind of graphs to be able to tell and give you information about what's going on with the reaction and its rate. Any questions about that? New set of formulas, good fun times. And we all got through here to initial concentration, what it means, right? All right, so let's look at the graph. Okay, I have that backwards. All right, here's the graph. I actually put it in your notes for you so you didn't have to draw it. As you can see, what's going on here on the Y, okay, we see it's the natural log of the concentration for the reaction. And you can see the data here listed as such, okay? Natural log versus time, that's going to be here, and you see it is a negative slope. So this really represents, negative K, because K represents the slope here. But as you saw in the equation, there's a negative sign in front of the K to make it positive, because you can't really have a negative rate constant. Okay? So when you graph it, you do the data, if you do the natural log of your concentration, you get the straight line like this. You know it's going to be first order. Okay? And pretty much that's what you're going to see. Now, first order and half-life again. Half-life, kind of the same idea as half-life in decay, when radioactive isotopes are decayed. But we're looking specifically at the concentrations, half of the concentration going away from the original. Okay? The reactant loses half of its original concentration, and it's the time it takes for that to happen. It's a nice little formula here, 0.693 divided by K. So this one doesn't depend on initial concentration at all, or any concentration at all, okay? So you will see that happening throughout the graph here. And you can derive this formula from the integrated rate law. So we can derive this. There's a nice little video I have that I found that derives it and uses pretty colors in a graph. And it's about 8 minutes long. You don't really need to know how to derive it, but if you're interested in why we have the 0.693 value there, we can watch it and you can see it, because I know you guys are all pretty math savvy here. Would you like to watch it, or no, or yes? Okay, we can do that. Is everybody done here, this slide? Okay, so there's the link if you want to watch it again. All right, first problem here. First order reaction is 35% complete. At the end of 55 minutes, what is the value of K? What do we do here with that? What are we going to do with the information provided?
Oh.
Yes, we have the time here. That's good.
No.
This 35%.
Put it in decimal.
So what could we do with that percent? When they don't give you numbers to work with, what do? You make up numbers. Yes, okay. Now what number should we choose to make up?
50.
You want 50 molar.
Oh, no. 1.
We're looking for, concentration here that we need to make up because we're starting at an initial concentration, but 35% of it's going away.
100. Oh.
Right?
100.
100. You want 100 molar. Once again.
Then I'll go to
1 sounds good to me.
1 and 100.
Although I will work it both ways. It is the same, well, sort of the same. If you use the 1 though, you'll see how part of the equation nicely drops off for you and makes it a little bit easier. However, we can work it both ways, okay? But do you get, if 35% is complete, that means how much is still around? 65% of the reactant should still be around, okay? Are we good with that? So if we make A initial 100 or 1 might be easier. We'll make it 2 sig figs and we'll make that a 3 sig figs for Nathan, right? Sig figs. There you go. Okay. Alright, so what's our equation again that we're going to work with?
1/2 equals 0.6
That's
factory over K. Natural log.
we're looking for K.
That one.
We don't have the half-life, so we can't use the half-life
Natural
line.
log of AX equals initial K plus the initials.
Okay, this is the first order integrated rate loss equation. We do know T because it's 55. We don't know K, that's what we're trying to solve for. And we've made up numbers now based off our 35% that we can use in here. So if initials are these, then this one after 35% is complete should be what? 65, right? Still sticking around? If you were doing the smaller number, which like I'll show you will drop off and be more easier for you. Yes, would be 0.65, right? Although on the multiple choice and things, you just make up easy numbers to work with. That's what you do, okay? So you can do what they also did in the video there to make it easier for yourself of the 65 over the 100. I guess make the bracket bigger there. Right? You can do that. You can do that natural log property if you want to. The natural log, though, of 1 here is going to be what? 0. So you see how that drops off if you use 1? So you could do that way, too, if you were doing the other one. So it'd be the natural log of 0.65 because this part is the natural log of 1. It's going to drop off. Now also, when you're calculating this, you need to be very careful about your K units. They're very picky about the K units. You remember the K unit stuff. How do you figure out the K units?
It's like M to the minus 1, whatever you had or something.
Okay, so we have 1 over M to the N, big M, sorry, minus 1 times the time unit. In this case, our time unit is minutes.
Oh, this is.
So we know what type of order this is. What kind of order is this? It tells us it's a
First order.
first order. So this, if we're doing the k units, becomes 1 m1 minus 1, right? So the m drops off, and we just have 1 over minutes. And if you don't like writing 1 over minutes, you can always do minutes to the negative 1. But they will expect your k to have the proper units. So if you're doing a second order, guess what the units would be on the bottom there?
M minus 1. No, that'd be molar minutes.
It would be m minus 1 times minutes minus 1.
Yeah.
Yes. You would have 1m on the bottom if it was second order. Does everybody understand that? Okay. So what does k end up being? Do we solve for k? Shouldn't be negative, right? Because the natural log should have changed that out. There shouldn't be a negative. What should it be?
Yes.
Times 10 to the negative 3, and then once again, it's going to be minutes to the negative 1. It's probably easier to write it that way. Okay, so now that you know k, it's a good thing. Okay, so let's look at the next one. One more. There we go. All right. Half-life tells you in the problem for a first order reaction that starts with 1.0 molar solution, and here's your k value. So it tells you this is a half-life problem. You can use the half-life equation. In this case, I'll just put in the k right now.
I'm really bad at
Okay. So what do we end up getting for our time here? Half-life time is, what'd you get? 53 seconds is correct. Pretty simple. Nice and straightforward. First order half-life was very simple and easy because there's no concentration involved. It's constant, remember? It's a constant value. Okay? Because the half-life on the 0 order and the second order are going to be a little bit more complicated. Okay? So, half-life, 53 seconds again. Now for second order. New equation, new formula. Oh, sorry, I do want to back up just for a second. I forgot to write this down for you. But just like before, that's half-life. Just like before, on the other one, we said no change, same change, square of the change. This one you need to think of in terms of natural log of the concentration versus time. That's always going to be first order, okay? So if you want to think of that as the quotes here, natural log of concentration versus time, that's your first order comparison, okay? That's what you're always going to be looking at, okay? Because second order is going to be the inverse of the concentration versus time. So if you can remember which one you're dealing with, you can remember the orders that you'll be able to find them quickly, okay? So just add that little tidbit in, and we'll go back to second order. Just ln versus natural log of the concentration versus time. And here, we would consider this one for second order going to be the inverse of the concentration versus time. As you see, it's going to be inverse of the concentration. You can tell in the formula right here. Kind of the same idea here, different variables in different places. Once again, you would graph the data, and you'd be looking at the data. This being, the T ones here, okay? However, the graph, this one, which you should see on your paper, which we'll see in the next slide, is a positive slope. So the K right here doesn't need the negative in front of it, because before it was a negative slope, so you needed that extra negative to change K into a positive number. Okay? But the variables pretty much stay the same, so you probably don't need to rewrite this every single time. Okay? They're just in different spots now, okay, in the formula. So make sure you have the formula down. That one is on the formula sheet, so that one you don't have to memorize. The half-life of first order and first order are both on the formula sheet. You don't have to memorize those either. Okay? So now looking at the graph here, and I put this one up here to compare to because this is the natural log of the concentration. This one is the inverse of the concentration on the y there. As you can see, one of them is a straight line. The other one is not a straight line. So when you're looking based off of the data versus time, you stick it in your calculator, you put all three in there, whichever of the three graphs comes out to be the straight line, that's the order. So because the inverse one is coming out to be the straight line here, this one, you see the straight line, we're going to know that it's the second order is going to be that type of rate off. Where here it's curving, it's not a straight line. Now, if you type in all the same data and this one came out to be a straight line, and it was the natural log of the concentration, then it would be first order. Okay? Does everybody understand why we're talking about straight lines here now? Half-life. It has its own half-life equation too, or formula. As you see, it's more in the inverse type of fashion here. 1 over the rate constant times the initial concentration. Now you see that concentration is playing a factor here. And let's talk about why that is in a moment. So go ahead, take a moment to write that one down. Yeah, so half-life does get longer. Make sure that you make the note, and it is a doubling effect. Half-life is doubling the preceding one. So if your half-life was 5 seconds, the second half-life would take 10 seconds, and then the third half-life would take 20, and so forth. As you see, it's going to double each time, and the increments would get wider and longer. Now, because the concentration of the reactants are decreasing at a quicker rate, obviously you would see that they wouldn't be able to half as quickly each time, so it would take longer for that to occur. Okay? Good? So here's a fun, nice problem to solve. Pay attention to your half-lives. This was actually very confusing because it's 25 and 50, so just know that this is an increment of 25. The next one actually is 50 long, so it is doubling here. Okay? So your first half-life here is 25 minutes. The second one, though, is much wider. It takes 15 minutes to go to the second one. Okay? So this would be second order. And obviously, if this was second order, and here's our only reactant is A, and just showing you A going to products here, what would be our rate law? K times what? Concentration of A squared. Good. Or A to the second. There you go. Now, you take some time, go ahead to figure out K and A when T is 525 minutes. We do know the initial, so we can have K here is 5. We also know the half-lives. What is it at the initial? The first half-life was 25 minutes. So what can you use there? The half-life equation to find K. Like so, and then all you have to do is plug in the values and solve and isolate K. So we get 5.0. Oh, and watch the units again on the K. Oops, time goes here, sorry. 25. And more minutes. And the 5 goes down here. Okay. Good with that? So what do we get for K? What did you get? 925. Does everybody know how to rearrange so that K is by itself? Because these ones are confusing because the variables are on the bottom. So this really ends up being like so. If you're isolating correctly. So our K then becomes now what's the unit on the K? M minus 1, good.
Minutes minus 1.
Minutes minus 1, good. This is second order, so you have to have 1 M on the bottom. Okay? Going to use the integrated law here. And that's KT plus over the initial, right? And once again, our initial was 5. We know our K now because we calculated it. But I didn't leave space for my time in here, did I? So this is 525. So our concentration now ends up being what? When you rearrange and solve, the concentration at that time ends up being 0.23 M. Good. And obviously the concentrations are going to be in molar. Yes. Answers, as you see. 0 order. 0 order is going to be concentration versus time. Okay, so this is 0 order. First order was the natural log of concentration versus time. Second order, once again, was the inverse of the concentration versus time. 0 order is just solely the concentration versus time. Okay? As you see here. Okay? So let's look at that one. Everyone's got the equation down now. Let's look at the graph. Okay, as you see, it's similar to the natural log one. Actually, the slope is the change in concentration over time, which gives you the negative K value, as you see. Okay, sloping downward, the plot of concentration versus time. Okay. Now for the half-life. A little bit more confusing, where you have the concentration being divided by 2 times the K, or the rate constant. Half-life now is going to get shorter as the reaction progresses. As the concentration of the reactants decrease, your half-life actually gets shorter. So now instead of second order where it was doubling, now it would go from like 10 to 5 to 2.5 and so forth. It would start decreasing. So those intervals become smaller of the time. Okay, so sample 4 here. Try to ignore the answers already, but see if you can work and figure them out as you're using the different equations. Okay?
No way.
Okay, so you got 4.7.
Yes.
Set up the 0 order. First order. Natural log now.
Yeah, the 1.5. No, I was just already.
So this is just plugging them in and solving. Basically, this would be first order. And then last but not least, second order. Using the second order equation. Now, one thing to note is the K units. Obviously, here the K units would have been 1 over just, I think it was seconds in that problem. No, sorry, for 0 order, it actually would have been m over seconds, okay? And for first order, it's just 1 over the seconds, and here it would have been 1 over times, with that, it's over, so there. Okay, so keep that in mind that the K's units would be different per equation there, but it says at the top just use the K units that would go with each one to make it work. Okay, by realizing that the 0 order is molar over second, it is just the slope, it's the change of concentration over time, so it is m over seconds there. Okay? So keep that in mind. Now for the fun graphing calculator problem. So you need your graphing calculators out. Oh, concept check first. So we'll probably just get through this today, and then we'll go on to the graphing, although you're welcome to try it on your own if you'd like to follow the instructions. It's pretty simple. How can you tell the difference among 0th, 1st, 2nd order rate laws using graphing, when graphing, supposed to be using, when graphing concentrations versus time? What are you going to see in the graph specifically?
The slope and the...
No, now we're graphing just regular concentration versus time. We're not doing natural log, we're not doing inverse, but how should they look though if you were just doing regular concentration versus time?
One's the 0 and then the straight and then the 0 slope, positive slope.
Okay, once again, we're talking about just concentration. We're not doing natural log or inverse.
It's not right there.
That's the rate one. Rate versus.
Only one that's just concentration.
So concentration versus time. Yes, for 0, you saw it, right? That one was already graphed for you as concentration versus time. And it just went like this, right? But if we were just doing concentration versus time for first order, how would it look? It wouldn't be a straight line, right? It's going to do what, Noah? It's going to decay. It's going to curve, right? But how does the second order look different from the first order in that respect?
Magnitude. A longer.
Steeper slope? Steeper slope for the second order. They're both going to decay, the first and the second. But, so, basically, here's the information. First order is just going to have the straight line with the negative slope. 0 order is the straight line with the negative slope. You're going to have the natural log function. It's going to look like a decay, but the second order has more of a steeper slope for the decay. So here, if you'd like to draw it versus write it, okay, I think that is a lot easier to mentally process. Straight line. Okay, this is, remember, just concentration versus time, not the natural log of the concentration or the inverse of the concentration. We're not trying to tell. If they give you concentration versus time, though, and 3 graphs like this, one steep, one kind of, and one straight here in a multiple choice question, you should be able to tell which one is which order. Like I said, the graphing part of the multiple choice here is going to be the most confusing because there's so many different variations of what they're putting on the y-axis here. So if it's just concentration versus time, 0 is going to be a straight line. First order will be a decay curve, but the second order will be even steeper on the slope there. Yes?
It's going to be different if it was like the natural log concentration than the first order would be straight.
When we're actually going to be given the data set, which you're going to see here, this data set, we're not going to have enough time to do it today, but we're going to actually plug all the data set into the calculator. We're going to do the natural log, the concentration, and the inverse concentration, all against time to figure out which one forms the straight line. So that's how these problems work. You have to actually plug them in. And if you follow, you can follow the ones, the steps on you probably already know how to put it in the calculator better than I do, because you've been in these math classes where you have to do this stuff. But you'll use the lists, you'll use the stat button, and so forth. But we'll get on to that next time. Okay?